Hey guys, it's Miss Hill and we are continuing our unit on linear functions. Today we're going to talk about linear programming that is nothing more than an extension of our system of linear inequalities that we were talking about yesterday. Linear programming is something that you'll see out in the business world. Businesses use linear programming to figure out how to maximize their profit or minimize their cost, because they do have limits on time and resources. So they want to make sure they're making the most money at the smallest cost. And they're able to do this because of the vertex theorem. And reading through that, it sounds very wordy, but when they're talking about the maximum or minimum value of our function on the polygonal convex set occurring at the vertex, it's nothing more than any point that is in the region that satisfies each of the constraints. That's going to be a solution. However, if you're looking for the minimum or maximum value, that's going to come from the vertex of the feasible region. And that's going back using the vocabulary that's at the beginning of your packet. So make sure you're studying your vocabulary. Now, if we want to find the maximum or minimum values given our objective function, what it is that we're trying to find, in this case for our first example, p equals 2x plus y, under our constraints, the first thing you want to do is graph all those constraints. And you can see I already have those graphed. It's just graphing our systems of inequalities. Looks very similar to what we did yesterday. All we're going to do in addition to what we did yesterday, our step 2 will be to find the vertices. So we want to see the points, or the vertices, of our feasible region. Well, what in the world is a feasible region? What am I talking about? Well, I'm talking about where everything overlapped with our shading. So we're talking about this figure right here, where everything overlaps. So anything that's in the blue is a solution to our system of inequalities, but we're looking specifically at these points where all of our inequalities overlapped. So we want to take those vertices, or those points, of 0, 0, 1, 0, 2, 2, and 0, 4. And once you have those vertices, you're going to come up here for your last step. The last thing that you want to do is substitute those values from the vertices into that objective function, or the equation, to find the maximum or minimum. So substitute your vertices into the equation. To find the max or the min. So all that means I'm going to do is take that objective function of p equals 2x plus y and substitute in each of those values for my vertices. So if we start with 0, 0, then p is going to be equal to 2 times 0 plus 0, which is just 0. If we're talking about profit, there's no profit. If we have the ordered pair 1, 0, then p is going to be equal to 2 times 1 plus 0, which gives us a value of 2. At 2, 2, then we can say that p is equal to 2 times 2 plus 2. So our value there would be 6. And then our last vertex, 0, 4, we would say that p is equal to 2 times 0 plus 4. So our p value is 4. So if we want both the maximum and the minimum values, we can see our smallest value, the minimum, was 0. So our minimum is at 0, 0. Our largest value was 6. So our maximum occurred at 2, 2. All right. We'll do one more of those and then we'll actually apply this to a real world situation. So looking at number 2, we want the minimum value with our objective function p equals x plus 2y under the constraints 2x plus y is less than or equal to 6 0 is less than or equal to x, which is less than or equal to 1, and then y is greater than or equal to 2. So starting at 2x plus y is less than or equal to 6. We're in standard form, so I'm going to use my x and y intercepts. So my y-intercept is going to be up here at 6. X-intercept will be over here at 3. And it was less than or equal to, so that means since we have that or equal to, we have that solid line. And then it was less than, so shading below. Now we're not in slope-intercept form, so again, if you're not sure, take that test point of 0, 0. 2 times 0 plus 0 is 0, which is less than 6. So yes, I'm shading in the correct direction. All right, let's skip down to y is greater than or equal to 2, and we'll come back to that middle compound inequality. If we have y is greater than or equal to 2, remember that's our horizontal line passing through 2 on the y-axis. We have that or equal to, so it's solid, and we're shading above. Now, going back to our 0 is less than or equal to x, which is less than or equal to 1. That compound inequality, x is between those two values. So that means that x is greater than or equal to 0, as well as less than or equal to 1. So we can draw those two boundary lines. They are solid lines because we have the or equal to. And greater than 0 but less than 1, it's everything that's in between here. So when we go to find our feasible region, so we can get those vertices, we'll highlight. We have this nice trapezoid here. So our vertices that we're going to use, our feasible region, has the vertices that are at 0, 2, 1, 2, 1, 4, and 0, 6. So when we go back to that profit or the objective function, and we're looking for the minimum, so we're going to use p equals x plus 2y. So at 0, 2, we would say that p is equal to 0 plus 2 times 2, and that's going to be equal to 4. At 1, 2, we have p is equal to 1 plus 2 times 2, and that's going to give us 5. Then over at 1, 4, we have p is equal to 1 plus 2 times 4. Well, that's going to give us 9. And then at 0, 6, we have p equals 0 plus 2 times 6, which will give us 12. Now our problem was asking us for the minimum value. So the smallest value was 4, and that occurred at 0, 2. So how in the world is this used in the business world? Well, let's look at this example where we have a manufacturing company. They're making TVs. So if they make a $60 profit on each console TV, $40 profit on each of the portable TVs, we want to know how many console TVs, how many portable TVs should be produced each day to make a maximum profit. Now remember, we said there are limitations that companies will have based on what they're working with. So keep in mind, making each of these TVs, it's going down the production line. And one of those console TVs requires 1 hour at machine A, 1 hour at machine B, and 4 hours at machine C. Each of those portable TVs requires 2 hours at machine A, 1 hour at machine B, and 1 hour at machine C. Now those machines, we know how technology goes. If you don't maintain them, it's not going to work properly. So we do have limitations with those machines. Machine A can only work for 16 hours a day. Machine B can only work for 9 hours, and machine C can only work for 24 hours. So we want to keep all of that in mind. Now, this is a whole lot of information, so let's break it down step by step. First thing we want to look at is what is the goal of this problem? What is it that we're trying to find? Well, we always want to make the most money, right? So we're looking for how many console TVs, how many portable TVs to maximize profit. So how many of each TV will maximize profit? Alright, so just like any other word problem, we need to assign variables for the quantities that we're trying to find, those TVs. Now when you're working with linear programming, these variables are what we call decision variables because they're representing the quantities that the company can decide to change. You get to decide how many of each TV, so it's a decision variable. Well, the TVs that we're looking at are the console and the portable TVs. So if we let X be the number of console TVs and let Y be the number of portable TVs, then that's going to help us organize all of our information in a table so that we can figure all of this out using our linear functions. So remember we said console TVs was X, portable TVs is Y. So looking back at our information, to make one console TV, we need 1 hour at machine A, 1 hour at machine B, and then 4 hours at machine C. To make one portable TV, we need to spend 2 hours at machine A, 1 hour at machine B, and 1 hour at machine C. Now the machines are limited, so this total we're talking about the number of hours for each machine, so the total time per machine. So remember machine A, that one was limited to 16 hours. Machine B was limited to 9 hours, and machine C was limited to 24 hours. And then our profit, going back to the original, the very first part of the problem, we can see that we make a $60 profit on each of those console TVs. And then we make a $40 profit on each of the portable TVs. So we're talking about money there. Okay? So, the way we've set up the table, we're looking for that profit. That's what we want to maximize. So our $60 for each console TV plus $40 for each of the portable TVs, that's going to give us the total profit. And that's how we're going to get that objective function. So we would say that P is equal to 60x plus 40y. So there's the objective function. All right. So now remember that there are limitations. Looking at machine A can only work for 16 hours. Machine B can only work for 9 hours, and machine C can only work for 24 hours. It can work all day. That one's the good one. Not much maintenance required there, huh? So, manufacturing companies, they cannot make as many TVs as they want because they are limited by those number of hours for each machine. So since they are limited by the number of hours each machine can work, So those limitations are the constraints. It's what limits us or keeps us from doing something. Now there will be common sense restraints. Remember those decision variables, the different types of TVs, they will be limited to. Common sense will tell us that we have to make some TVs to make a profit. So let's write all those constraints as inequalities. Going back to those tables, looking at each of the columns, if we look at the column for machine A, that's going to give us our first constraint. So we had our 1 hour for each console TV, and then 2 hours, oops, we forgot the X, didn't we? So 1 hour for each console TV. I don't need the 1 there. Plus 2 hours for each portable TV. We're limited to, so it's going to be less than or equal to 16 hours a day. Then if we look at our column for machine B, we only need 1 hour for our console TVs, and then that one takes 1 hour for our portable TVs. Machine B can only work up to 9 hours a day. So we have x plus y is less than or equal to 9. And then machine C, spends 4 hours working on a console TV, but only 1 hour working on the portable TVs. And that one can work 24 hours a day. So we have 4x plus y is less than or equal to 24. Now remember those common sense constraints that we mentioned. If we're talking about the number of console TVs and the number of portable TVs, we cannot have a negative number of TVs. It doesn't make sense. So common sense would tell us, so we want to include x is greater than or equal to 0. Remember that's our number of console TVs. And then y also has to be greater than or equal to 0. That's the number of portable TVs. All right. So if we were looking at some possible values that would satisfy each constraint, we could say one of each, or 1, 1, if we wrote it as an ordered pair. We could say that we want, what else would work? Maybe 3 of the console TVs and 2 of the portable. If we went back to plug that in, would that work? We won't write that one as an ordered pair. So 3 X's and 2 Y's, so 3 consoles and 2 portables. We could sit here and work through using each of our constraints, saying do these values work with everything? Or we can represent all of those possible values and figure out visually much easier by simply graphing all of our constraints. So let's start with our first constraint, machine A, at x plus 2y is less than or equal to 16. Now I'm in standard form here, so I can find my intercepts and say that my y-intercept for machine A will be at 8. So I'm up here at 0, 8. And then my x-intercept would be all the way over at 16. That goes off of the grid. So I can switch it to slope-intercept form real quick and find that my slope is negative 1/2. And then that makes it easier to graph. So there's those points. We have that less than or equal to. So we have the solid line. And it's going to keep going that way. And it was less than, so we want to be shading below. And then we'll repeat with machine B. That one's very easy to find our x and y intercepts. They're both at 9. And then we can connect those 2 points with a straight line. And that one was less than, so we will shade below. And then for machine C, we can see that our x-intercept is at 6. And then our y-intercept is all the way up at 24. So a quick conversion to slope-intercept form, we have a slope of -4. And I'm going to count backwards and go up 4 to the left 1. And then we'll connect those points with a straight line. That one was also less than, so we will shade below. All right, and then don't forget about those common sense constraints. Remember we said x has to be greater than or equal to 0. So we're shading above here. And then our y is greater than or equal to 0, shading above here. So where everything wound up overlapping, we'll highlight that in blue. And here is our feasible region. I'll emphasize the blue there. So anything that falls in that blue area. So our 3 of the console TVs and 2 portable TVs, it's in that blue region. So then that is one possible combination. But it's not going to give us the maximum profit. So remember we said we want those vertices of the feasible region. So let's list those points here. We of course have the point 0, 0. Then we have the point here 6, 0. And this loveliness here, we have 5, 4. I think I might erase some of those drawings that I have there. And then we have 2, 7. And our last vertex is at 0, 8. And we'll erase some of this just to make things a little bit easier to read. Oops, didn't mean to erase my line there. There we go. Alright, so now that we have our feasible region, how are we going to use that to find the maximum profit? Remember we talked about all those ordered pairs? So we're going to use the ordered pairs from our vertices on that feasible region that we talked about. Whoops. Vertices. So using the vertices that are on the feasible, or the graph of the feasible region, what satisfies all the constraints. So ordered pairs from the vertices on the graph that satisfies all constraints. That's our feasible region. Alright, so remember that profit equation that we wrote? Our objective function we said was P equals 60x plus 40y. So we're going to use that with each of our vertices and see what we get. So of course at 0, 0 down here, P is going to be equal to 60 times 0 plus 40 times 0. Makes sense that our profit would be $0 if we made nothing. At 6, 0, our profit would be 60 times 6 plus 40 times 0. So we have a profit of $360. Over here at 5, 4, our profit would be 60 times 5 plus 40 times 4. And that's going to give us a profit of $460. to 7, our profit would be 60 times 2 plus 40 times 7, giving us a total profit of $400. And then last but not least, at 0.8, our profit would be 60 times 0 plus 40 times 8, giving a profit of $320. So looking at all of those, we want to see which one is the highest maximum profit. So our max profit is going to be equal to $460, and that occurred at 5.4. So what does that ordered pair 5.4 means? Well, it means that we want 5 of the console TVs and then 4 of the portable TVs. So making 5 console TVs, 4 portable TVs gives us a maximum profit of $460. All right. So in your packet, you will see this box that reminds you of all the steps that are used with linear programming. So remember, first thing you want to do is define your variables, those decision variables. Identify which quantities, what do you want to maximize or minimize. Write that profit equation if that's what you're looking for. So that's your objective function. It might be for the lowest cost, but you're going to write the objective function. Then you'll write your constraints. Don't forget those common sense constraints. Very important to remember those. Then you're going to graph all of your inequalities. Look for where it overlaps. That's your feasible region. Find those coordinates. And then you're going to substitute each of those coordinates into your equation or that objective function that you wrote. And then you're going to pick which one gives you the maximum or minimum depending on what it is that you're looking for. There's some more practice on this page that you can work out and check your answers on Blackboard. Don't forget to finish your homework. You can check those answers on Blackboard as well. If you have any questions, send me a message on Remind or email, and I will see you in class tomorrow.